All right, so this brings us into how do we get the most spectrum of light, bang for our buck electricity production from solar panels? You're going to watch the 101 videos and they'll talk about what great solar potential there is. So photovoltaics are an easy answer to move towards, but the technology itself has developed over time. And the first form of the technology was the gelatin pour, where it was just silicon with a circuit running through it. We would collect wayward electrons, and it worked fine for very small things like that little calculator, that small toy. Now we are able to do crystallines. Crystallines could be set to specific light spectrum collection, which means that we were going to collect the most useful or abundant spectrum part of sunlight. So sunlight spectrum, once again, goes all the way from our gamma rays all the way up to AM, FM waves, right? So very big things in my electromagnetic radioactive spectrum. I only want what is most abundant from the sun, which happens to be ultraviolets into near infrareds. Under that, the thing that is most abundant is things within the visible spectrum, so Roy G. Biv. When I go to pour my silicon, I will specifically pour to collect within the low end of my Roy G. Biv spectrum. So my blues, greens, purples, and violets in my structure. And while that is great, it really is limiting. And there is an answer for that. But the most common type of photovoltaic cell, the lightest form of it, if it is a crystalline structured silicon pour, will be a single junction, which will be collecting the visible spectrum of light. Here's a little bit on that visible spectrum, just talking about the band gap. What happens is when I heat up my silicon and I melt it and turn it to liquid, when I go to pour it back, I set it to a frequency of vibration so that when it becomes crystalline solid again, the cells of the silicon will be spaced exactly far enough away that when sunlight strikes my cells, the electron will be able to jump the valence shell distance from one to the cell next to it, allowing it to have electricity, right? Because electrons jumping valence shells. And that's called the band gap. Different spectrums of light respond better with certain band gaps. So I set a frequency to do the visible spectrum of light when I pour, and it allows me to collect this. This also means that things that aren't just silicon can be used to make a solar cell. A lot of metallic bonded things, so things in the metal family of elements, can be utilized to make electricity. The thing that is easiest to manipulate, least expensive, incredibly abundant, is silicon. But there are other things. There is a class that's been going on right now out of the Norwegian part of the world about organic solar cells. And those are offered actually free. So if anybody's curious, look them up. And they are looking at things that are not silicon to make solar cells out of. But right now, we use silicon. It's abundant. It's easy to manipulate. It's not expensive to come by. It just makes sense. However, with that said, you can see where only being able to collect one part of the visible spectrum is not helpful. It doesn't get you enough bang for your buck. And it's great for something small like a house. But to really get some bang for your buck, you need to get more than just the visible spectrum of light. And so that brings us to the next part of these cells, which is multi-junction. Now, multi-junction have the P and N stacked on top of one another, responding to different light spectrums. So for example, in a multi-junction, I will make different silicon pores of P and N types with their band junction in between, and I will put it on top of another one that will respond to a different spectrum of light. And these things are wafer thin. They're very, very thin pores, but we're allowing them to structure and stack. And the way we stack them is based on high frequency. So it's my high energy material, and it's going to move to the longer wavelength, lower energy material. So on top, I'm going to put things that will respond to ultraviolets. So my UV pore is on top. Then my visible spectrum blues are below that. Then comes my yellow spectrum. Then my orange and reds. then my near infrareds. And then just to get the bang for my buck, I'll put my thermal infrareds below that so that if my solar panel has been all warm all day long, I can still absorb a little bit of that thermal infrared energy that's radiating off of the material later on in the day. And so that allows me to structure. And that's a multi-junction. So the light will hit it and it will either respond or it will continue through this wafer-thin material down to the layer that it will respond to. It allows for a lot of ability. It allows for more collection. On the other hand, these are heavier objects. They're heavier, they're more expensive to produce, they're not viable for your home rooftop solar. What they are viable for is making power on large scale. This is when we're talking about solar farms, places where we're going to have a solar grid hooked up to it. Multi-junction devices, talking about the stacking and how I want to collect UV into visible spectrum into some of my infrareds. Obviously, they're showing you that peak sunlight material is right here in the blues portion of the spectrum, which is why if I'm going to make a single junction, I'm going visible, purple, blues, greens. A stacking module to try to show you if I stack it, right, on top of one another. This is the silicon pores and how they're responding to different light spectrums. And then notice how thick these versions of the panels are compared to the wafer-thin versions of the panels, which would be in a single junction module. Just talking a little bit about what happens when the light strikes. We've watched the video on what happens when the light strikes. So let's look a little bit on installing, and I'm going to show you some pictures of my home. So here we go. Here is the photovoltaic system going on my home. I've done small scale projects. Obviously, for something to go on my roof, I had the professionals come in. I also was going to be grid tied, so I do not have a battery bank on my system. My system goes directly out onto the grid, and the power company pays me for making power. And when I use the power company's power, my meter goes in reverse, and I have to pay them. And by the end of the year, sometimes I owe them 20, sometimes they owe me 20 bucks, but we're pretty much net zero. And I've had this system for 5 years now, so I can speak from a place of knowledge where I'm coming from in this. So here they are putting down the bracket system for the panels. Now, when they drill through, they do sometimes crack, and so they will gel them suckers up. But here we go. There is a cracked piece of my asphalt roofing shingles, right? So they're going to do that. And cracks happen. Can't feel bad. Just make sure that you silicone them up. Be honest with homeowners, so on and so forth. Here is the array of panels once they clicked in. Here we go. The array of panels. Yes, I went up on my roof. Here's the array of panels up on my roof when it's completed. And that got run down into the house, and it got run into my inverter box and my charge controller, and that is this structure right here. And a little bit on that, I will show you more on this sort of thing. I'm also going to show you how to circuit up a very simple panel so that if you want to hook up something small in your home, you can do it too. I don't want you to think this is something that's beyond the means of every single individual to do. So, and here is my external power switch as well as my internal power switch. And the reason for that is in the state of Connecticut, we are legally required to have both an external and an internal shutoff system for our power, right? And that's my circuit box. So using my breaker box. And then my generator override. Here is the plugs for my car because I have an electric car. So, you know, got to have these things. Here is the concept of doing parallel circuiting versus a straight line of circuiting. If I do straight line circuiting where I'm doing each module running into one another and I shade out one part of the module, I will shut down the electricity from traveling into the line. Where if I circuit each module in a parallel by itself, it allows me to constantly generate electricity even if the middle one is being shaded. So on that note, I'm going to pick up with the build it yourself version in the next video, part 3.